Hello friends, today I'm going to be teaching liquid pressure and depth relationship, the thrust and the effects of water or of liquid in sounding pipes on tanks. So the first thing I'm going to try and achieve is to determine the relationship between liquid pressure and depth, is to determine the thrust on the area of the tank, and also to determine the effect of water in sounding pipes on tanks. So first of all, I would like to mention these three observations about pressure in a liquid. First of all, we understand that the pressure on a horizontal surface, which is under water, is equal to the weight of a column of water above it. So what we are trying to achieve is, so let's say we have this tank. Okay, we want to show, and then let's say we have water here. It could be water, it could be any liquid. So we want to show that the depth here from the surface. So when I say depth, so I'm referring to from the surface of the liquid down to reference point, determines the pressure at that point. So if I choose another reference point, the pressure at this point depends on the depth from the surface. So if I choose the bottom of the tank as well, what I'm saying is that the pressure at this point is dependent on the depth from the water surface. Okay, that's what we want to prove. Okay, so the first statement is the pressure on a horizontal surface which is underwater is equal to the weight of a column of water above it. Okay, so that's the first thing we want to prove. Okay, so from the basic physics theory, we know that when pressure is acting on a surface, when force is acting on a particular surface, let's do it in this form. Okay, when a force is acting on a particular surface of this area, okay, we say that pressure is equal to the force divided by the perpendicular distance, perpendicular area. Now, however, when we are talking about fluid, we are considering the weight, okay, of the column above the column of water above that point. So if I'm considering this point, for example, so it's going to be the weight of the fluid that is exerting pressure at that point, okay, at that level. So instead of considering the force, we say the weight, okay, the weight of the fluid, okay, above the column, the weight of the column of the water above the reference point. So divided by the perpendicular area, okay, which is simply the same thing as W over A. Okay, so we say pressure now. So we say pressure is equal to weight over area. So weight of the fluid, okay, above the reference. Now, also from the basics, we know that weight is equal to mass times acceleration due to gravity, okay, which means W is equal to mg. So let's keep this equation as equation 1. Okay, let's keep that, or let's call this equation 1 and let's call this equation 2. Now also, so we have two equations. So also we know that volume of any prism is area times height. So what that simply means is the base area of any prism. So if it's a cuboid, cylinder, pyramid, or any sort of three-dimensional shape, the volume is area times height. So in this equation, so I have W here, I have A here, okay? Now, if I bring this down, so I have pressure to be equal to my weight is mg, okay, over, so let's call this equation 3. So my weight is what? Mg from our equation 2. Okay, so now our area from equation 3 is actually V over H. So how do I get that? So if volume is AH, A will be V over H. So we can then substitute that into equation 1, and then we get the area to be V over H. So I can now say area is V. I'm going to open a big bracket over H. Now what this simply means is that pressure is mg divided by V over H. Now inverse multiplication means this division is going to become multiplication, and then we inverse what next after it. So we have pressure to be equal to mgh over V. Now from the basic principle, we know that density is equal to mass over volume, so which is the same as rho is m over V. So it means that from this equation I can say, so m over V, then we have gh, so m over V is rho, so we substitute rho gh to be pressure. So the pressure is now, the final formula for pressure is now rho gh, density times acceleration due to gravity, times the height of the column of water above the reference point, which is actually the depth. Okay, so we can say that rho is the density of the fluid or of the liquid. G is the acceleration due to gravity, and h is actually the depth, okay, from the water surface, okay, from the water surface. Or we can say it's the height of the, we can say it's the height of the column of water above the reference point. So the density is measured in kilograms per meter cube, okay, or it can also be measured in tons per meter cube. Acceleration is measured in meter per second squared. The height is measured in meter. So this is the basics to show that pressure, okay, this is just to show that pressure is rho gh. Now the density, so if we have a water column and we have water here, okay, I'm going to do that again. So if we have water like that, we want to consider this water, or we can say if the fluid, okay, as some parameters. It has the density, it has, then there's an acceleration due to gravity, okay. Also there's height reference point where we want to consider the pressure. So let's say we want to consider point A, point B, point C, for example. So we have HA here. Then from the surface, if we are considering B level, is HB, and if we are considering C, is HC. Okay, so it's the depth. Now something is changing here. Acceleration due to gravity is constant and is acting downward, right? So it's constant. So let's represent all constants as K. Okay, let's constants be K. Okay, so acceleration due to gravity is constant, which is this here is constant. The density of fluid is constant as well, because we're not changing the fluid. It's the same fluid. We just want to know the pressure of the liquid at every point. So it's the same liquid, the same acceleration due to gravity. So the density of the fluid is not changing. It's also constant. Okay, and then the height is what is changing. Okay, it's the variable. So for every point in the liquid, for every level, horizontal level on the liquid, we have pressure. Okay, so for each point, so meaning that P, the pressure, is now constant H. So pressure is now directly proportional to H, because the rule is that K is constant, it changes to a proportion. So what does that mean? Pressure of liquid in a column is directly proportional to the height of the column above the reference point. In essence, what we're saying is that as h increases, the pressure also increases, meaning that as the depth keeps going down and down, if we keep getting to the bottom, it means the h is increasing because we're measuring from the surface, okay, since it's depth. And also, if we are going up, reducing the h value, the pressure is also reducing. Okay, now we have established that the pressure on the horizontal surface, which is underwater or any fluid of a given density, is equal to the weight of a column of water above it. Okay, so that's that. Now what we want to do is to determine the pressure, okay, in terms of tons per meter squared. Also, we want to determine the thrust. But first of all, let's consider the tons pressure in tons per meter squared. So we know that pressure is measured, is actually force over area, or we can say it's weight over area. It's measured in newtons per meter squared, or we can say in SI unit. It's going to be kilogram meters per second squared over meter squared, and then we can have it as kilograms per second per meter per second squared. Okay, this is another unit. But also we can say, instead of using the force, okay, instead of using weight, all right, we can consider that in terms of mass over area, okay, which can then be tons per meter squared. That's if mass is in tons, or if it's in kilograms, it's going to be kilograms per meter squared. So this is what we're going to be using going forward, at least for this class. So now we want to consider this column of water. So we're going to divide this into squares. Okay, we divide this into squares. Okay, so we have 1, 2, 3, 4, 5 squares. So I'm going to name this A, B, or I'm going to do it this way. Okay, so we say that this is a cuboid, okay, segmented into squares. Okay, squares. Now the square has a cross-sectional area of a square shape, which is 1 meters each side. Okay, 1 meters each side. But they are also, so before I move forward, it means the cross-sectional area, or we say the base area, is actually, since it's a square, then it's 1 times 1, which is 1 meter squared. Now these square plates are 1 meters away from one another, okay, which means that's the height. The height of each squares, they are 1 meters away from one another. So okay, so I'm just going to try and distinctively separate these boxes, just to indicate that they are different entities. And then so we have 1 box, 2, 3, 4, 5, and then I can also name it, call this I can call this plate A, call this plate B, C, D, E, and F. So we know that the plates are 1 meters away from one another, And then we know that it's a square plate, which means the area is 1 meters squared. So what is the volume of the enclosed cube? Okay, this cube, this cube, this cube, this cube. What's the volume of the enclosed cube? We need to determine that. So we know that volume is area times height. Okay, so it means that V, if we are considering the volume between A and B, okay, so it's actually area is 1 times the height is 1, so that's 1 meters cube. If we consider the volume between B and C, between A and C, you know, now we're going a step downward, then it means the area is still the same cross-sectional area, 1, because the cross-sectional area is constant for all, so 1 times the height now between A and C. So it's now 1 plus 1 is 2, and then we have 2 meter cubed. Then between the volume between A and D, if we go down more, okay, we are increasing the depth now. Okay, we're increasing depth H, so it's now 1 1 1. So it's now the area is still 1, the cross-sectional area, but the height has increased further to 3. So we have 3 meters cubed. If we have VAE, no, it's going to be what, 4 meters cubed, and VAF is going to be 5 meters cubed, and so on. Okay, so that is the volume, okay, of the column above each reference. So if reference B, we want to know, determine the volume above this plane is 1 meters cube, above this plane C 2 meters cube, above this plane D 3 4, and so on. So what about if we determine the weight? Okay, because we're really interested in proving that the pressure on a horizontal surface which is on that water is equal to the weight, okay, to the weight of the column of water above it. So what I'm going to do is to determine the weight. So we know that density is mass over volume, okay, and then the mass is going to be density times volume, okay, mass over volume. Okay, so now let's come back to all of this now. Okay, let's come back to all of this, and then we continue with now mass. So mass AB will now be, you know, density times volume. So density times, what's the volume? Okay, the volume is 1 meters cubed. So the density is actually measured in, okay, I'm going to do this again. So the density is measured in density tons per meters cube, and the volume is from here is 1 meters cube, which is density tons. Okay, now if we go further here, the next step is to go downward, increase the depth. So it becomes M from here, MAC. So the density is density tons per meters cube, and the volume is 2 meters cube. So meters cube cancels meters cube. So we have MAC to be density tons, and there's two density tons. Okay, so meters cube and 2 times density is 2. Okay, now MAD should be density tons per meters cube times this time around AD is 3 meters cube. So we have it as 3 density tons. So what that means is that so if we consider AE, it's going to be 4 density. If we consider MAF, it's going to be 5 density, you know, tons and tons. So that's that. So what this means is that the weight of the column, actually, if you look at each of them, the weight of the column above the reference point is actually increasing as the volume, you know, because the volume is increasing as well. So it's the weight too is increasing as the volume of the column above it is increasing. So meaning that if I have an extended column down, you know, if I have this column extended downward, okay, and I want to know what is here, let's call this Z. So it means that the mass, the weight from the surface, okay, of the fluid, of the liquid, to the lowest point, which is the bottom of the tank, Z, is gonna be the height, AZ, which I don't know how long it is. So the height in okay, in meters times the density. Okay, so the height times, which is the height of the liquid above the reference point, or we can simply say the depth times the density. Okay, so the mass of the, or let's say the weight of the liquid column above Z is actually the depth from the water surface, to the Z level times the density. But don't forget that this is where we consider the cross-sectional area to be 1 meter squared, to be a square. Okay, and then to also, for simplicity, 1 meter squared. If we put that back, say we don't know if it's 1 meter each, if it's a square, then it's going to become A, right? Back, if we put it back there. So it's still going to be in tons, okay? Because this is in meters, this is in meter squared, this is in tons per meter squared, okay? Still going to be in tons. So this is in a case where we, for simplicity, that we consider a square area of 1. But this is in a case where we don't, it's of a different cross-sectional area. It could be a square, but just to make sure that it's not, 1 on each side. Now, we recall that pressure is force over area, is weight over area. And then we said, okay, this is if it's in actual weight. We can also represent pressure as mass over area, which is then going to be in tons per meter squared. So what we want to do is we want to project this weight of the fluid on the certain area. So for every particular area we consider, we want to know what pressure is exact. So pressure is then going to be the mass here. So mass over area, so which is the mass is AZ times A times density over A. Then A cancels A. We can say pressure is AZ times density. So I'm going to box this. It's very important to understand that pressure calculation is going to be the depth times the fluid density. Okay, so now the next is going to be thrust. So it's going to be fluid thrust. Okay, now fluid thrust is another word for thrust is force. So we can recall from previous discussion that pressure is force over area. Okay, so force, which is actually the thrust, is then going to be pressure times area. So pressure, we have our pressure from here already. So we just say it's a P, okay, pressure times area. Okay, that's just it. If we substitute, we can either use this formula, okay, or we could go further and say pressure force, which is the thrust, will now be our pressure is what? Our pressure is depth times fluid density times area. So we've been able to establish the two objectives. Okay, so that's that. However, there are some points I need to note here in order to help us in solving questions. Okay, number one is that, well, first of all, we have established that number one, pressure is, on the horizontal surface, which is under water, is equal to the weight of a column of water above it. The next thing I want us to discuss will actually be number two, which is pressure is the same. Pressure is the same at all points at the same horizontal level within a homogeneous incompressible fluid. And what that simply means is that if we have a container full with water, and we consider three, let's say we consider three different points. Okay, point A, point A, point B, point C, point D. What that simply means is, for this level, for example, level A, the pressure is the same. So it's going to be PA, 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 PA. For this point, every point is the same. So if the value is PB, it's going to be PB, 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 as long as it's the same horizontal level. And same thing for C, same thing for D. Okay, so the third thing about pressure, third discussion or analogy is, I'm going to erase this. So the third analogy is going to be the pressure acts in all directions, and they are the same horizontally, vertically, and oblique. And again, what that simply means is, if we have a tank as well, and then we have water or any kind of fluid. So if we take point A, okay, point B, point C, or even point 0, what it means is that this point actually has force acting in all directions, and they are the same. Same thing here. It acts in all directions, and they are the same. Okay, so let's say this is one of the points A, for example. So let's say it's one of the points. So we have one acting like that, and then downward, and then we have it like that, and we have it like that. So it's always acting in all direction, and it's all the same. Okay, so if this point is A, so it's going to be PA, 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 PA. So a reference is a point in a fluid. The pressure is acting in all direction. Now, going forward, another thing I want to point out is this. Please note that when you are calculating the pressure, okay, we said it's depth times the density of fluid. Now, please note that the depth is the depth from the liquid surface, okay, from the liquid surface. Okay, it's always the depth from the liquid surface. Okay, and what that means is, and then also another thing I want to point out is number 5, is that always consider, like, there could be two scenarios where you'll be asked to calculate. So let's say we have a 3D, for example, tank. So let's say this is a tank, or let's say it's a ship. You know, this, if this is a ship, we say this is the bulkhead, and then we say, if it's a tank, we say this is the tank top, right? Tank top. If it's a ship, we say this is a bulkhead. Okay, and then if it's a tank, we say tank top, and then if it's the bottom of the tank, we say tank bottom. So it's important to note here that, first of all, understand the question. So if it's a tank top, it means that we want to determine the pressure here. If it's a tank bottom, we want to determine the pressure here. So in that case, we use the cross-sectional area for, so these are the two formulas, right? Pressure is depth area, and thrust is a pressure area. So what is this depth? What is this area? So for tank top and tank bottom, your depth is the depth, okay, because the centroid is actually along the axis, vertical axis. So your depth is always the depth above the reference surface, okay, and because it's always facing forward, is the actual depth from the top, okay. So we don't divide, we don't multiply anything. It's whatever depth it is to the surface, and the area is the cross-sectional area of the horizontal surface. Now this changes when you are considering bulkhead. So for bulkhead, let's say we have, so the bulkhead depends on the shape, okay, to determine our D and A. So what does that mean? Now, if we have a water column, right, and we are asked to find, or let me use let's use something else. Let's use something like that, a 3D. Okay, so we consider this as our bulkhead. Okay, so if let's say water is there like that, let's say we have water like that. Okay, so we need to our D then becomes the depth from the water surface. It's no more horizontal like what we have here. Okay, now it's vertical. Okay, it's vertical, y, x. So it's vertical now. Okay, now the depth is now going to be up to the centroid, or the center of gravity of the bulkhead. That's going to be our depth. Okay, unlike the other one where if we want to consider, okay, the same even here, look even here, if we do this, even here, okay, even here, let's say this is water column, so we have to consider the centroid of this, which is also the height divided by 2 because it's a square. So when we are considering the depth, we are considering it from the water surface to the centroid, or we say the center of gravity of the vertical reference. So vertical reference I mean here is the bulkhead. If it's not a flat horizontal surface, then we always consider the centroid. And then we also consider the area of the bulkhead shape. So if it's a circle, it's by r squared. If the shape is a triangle, it's half base times height. If the shape is a rectangle or square, we say it's length times breadth. Yeah, and that's it. Okay, now, so now the next thing is to determine the effect of water in sounding pipes on tanks. This is very simple. So effect of water in the sounding pipes of tanks. So let's say this is a sounding pipe. So this tank is filled with water. This tank is filled with water. Now, but after it's filled with water, it starts to rise above into the sounding pipe. All right, and rose by h. Let's say h. Okay, the height in the sounding pipe. So when water rises in the sounding pipe to a particular height of, say, let's say height, h, above the top. So we say this is a tank top. Okay, and this is tank bottom. So above this top, water rises into the sounding pipe. Okay, pressure is set up on the tank top. So we have pressure set up here. We have pressure set up here just due to the the height of the water column in the sounding pipe. And don't forget the law we said, the rule here that says that pressure is the same at all points at the same horizontal level. Okay, same horizontal level within a homogeneous. So if we come back here, if we have a pressure here, say P, sounding pipe, it's going to be the same here, same based on that rule. So it's going to be P sounding, P sounding, P sounding on every level here. Okay, now, so the actual weight of the water here, could be small. However, its effect is very huge on this tank. Okay, this tank is designed for a particular pressure. So when the pressure here, additional pressure is exerted on the tank top, then it has in all the direction. Okay, it's transmitted all over the whole tank top. All right, and then it can actually cause this tank to collapse. Okay, this is why it's not advisable to leave tank tops pressed on, because this can exert stress on this tank, and this tank can actually collapse. So each time we're asked to calculate, we have a sounding pipe, we have to consider the P is equal to this, that, okay, the depth, let's say pressure at this tank is going to be the depth, which is the H, times the density. Okay, and that will be the end of this class. The next class is going to be you applying these things. We have these formulas, this equation, this theory, applying them to questions, solving several questions. All right, and thank you so much for paying attention. And I'm the one and only Gabson. Please remember to subscribe to my channel, encourage me so I can do more. I have so much that I want to deliver. Thank you, and have a good one.